Let's revisit this function we looked at earlier. Let's denote the domain set as x and the codomain as y. We can write the function, say f, being the function which maps the domain x to y with the rule defined as follows. By the way, it's common to refer to the elements in the domain as objects. Each object is then mapped to unique elements noted as image in the codomain. So, in this example, 2 is the image of the object 1 of the domain. 4 in the codomain is the image of the object 2 in domain. And 6 is the image of the object 3 in the domain. You can notice that we purposely chose the function as such that each image is twice of the object value. It is easier to have some form of shorthand for this. We write it thus: f of x is equal to 2 of x for all x in the domain. This is the symbol for all. However, to less complicate matters, we will omit this part, especially since most texts do not show this, as it's generally understood what x is in this context. Now, it's very tempting to actually draw a straight line through these 4 points. Please don't, because that would make it a different function. Let's graph that straight line function again. Notice again the domain and codomain of the function on the left, for which the domain contains only 4 elements. The straight line, on the other hand, consists of an infinite number of points, which means the domain itself has an infinite number of elements. Its domain actually consists of all possible numbers between 1 and 4, including 1 and 4. The domain of this function can be written as an interval. Notice the square brackets? This means the numbers 1 and 4 are included in this set. These are called closed intervals. The codomain too is a closed interval, which includes all numbers between 2 and 8, including 2 and 8. This is the main difference between our functions. Now, like the earlier case where we write the function f, we can also write this function, let's call it g, as follows. It maps from the closed interval 1, 4 to 2, 8 with the following rule. Notice that these two functions are in fact different. That's why we give it different names, f and g. We nevertheless maintain the x name for the elements in the domain. This is just a variable, so it's not a problem. Let's look at another example. This is another straight line graph, though this time, this straight line can be imagined to extend to infinity. The domain then can be written as follows, to include all possible numbers. Notice this time we use a normal parenthesis, not the square bracket. Infinity is not a number and thus cannot be included in any interval. This is called an open interval. The codomain is also the open interval of all possible numbers. We call this function h, and we can write it again as a mapping from its domain to its codomain, though sometimes some texts prefer to write it as such, i.e. the domain and codomain are all real numbers. This capital R thing denotes the set of all real numbers. This function is actually defined based on this rule, hx equals to x plus 1, which literally means every image in the codomain is really equal in value to the object added by 1. How about this function? It too has similar domain and codomain as the previous function, namely all real numbers. The rule for this function, say q, is given as q of x equals to the square of x, which means the image of the function is always equal to the square of its object. We will revisit these functions again in the next video to go into further details of functions. But before that, let's have a simple question to think about. Can you write these last two functions using the ordered pair representation? We'll answer this in the next video.